you, Maciek. I will talk about AI. I'll talk about challenges and considerations for real-time AI processing. So, as you may have heard, I am Wojtek, and I work at AI team at Software Mansion. Over the last year, we did a couple of cool projects, mostly regarding computer vision. We did XVision. That's like an Elixir package for running AI, computer vision models in real time. If you may have seen it since you're from the multimedia background. If not, check it out. We also did, this is the real-time inpainting video, real-time video inpainting app that I will focus on today. And more recently, we're focusing on AI on mobile. We're developing some kind of app that you can point an object and then erase it from existence. As you can see, we like to erase things. During my presentation, I will focus on computer vision and efficiency. If you've seen my talk from the last year, you might have noticed that I still talk about the same thing, but that's just because I like it. That's my thing. And I will not talk about large language models. I think we have all heard enough of them from the last 2 years already. So real-time AI, what do I mean by that? By real-time AI, I'm focusing on multimedia applications, like models that need to run on autonomous systems, driving systems like that need immediate feedback. It can mean like a segmentation model that's responsible for your background blur when you're at a conference call. There are many use cases like transcription or live translation apps being built. You may use some of them. Real-time AI is characterized by latency constraints. So how fast is fast enough to consider it real-time? We have a few use cases like live broadcasting, where a few seconds of delay of latency is fine. And if we want to run some AI magic, we can do server-based processing. We can just offload it to a GPU server. We do not worry so much about latency. Some people do not consider it real-time. Yeah, I think there's some truth to that. We have live conferencing, where I'm not an expert on that. I think about 250 milliseconds is good enough for a latency. And that solutions work better on edge, meaning if we want to run some AI stuff, like a background blur model, it works much better if we do it on edge, meaning your end device, like a smartphone or a laptop. Also, we have gaming and augmented reality use cases, where milliseconds matter, since we have to render stuff in real time, like basically instantly. And for those cases, we do not have any other option than to just deploy the models on edge. With edge processing, we have some advantages and some disadvantages. Obviously, I'm gonna go over the cons first. We have less compute power, so we are not going to fit large models like, I don't know, large language models. I know I lied. And they need to be energy efficient. If we're going to deploy something on your user's smartphone, we have to think about not draining his battery. And advantages, it's extremely easy to scale. You do not need to create any infrastructure if you're going to run it on your user's smartphone, for example. It's low latency as well. You don't have that overhead of communicating with the cloud. Yeah, so let me introduce you to real-time video inpainting solution we did like half a year ago. What's inpainting? I think you're all familiar with that concept. It's a computer vision task that's supposed to, fill in missing regions of a photo with something visually coherent. It's popular now because of the diffusion models. You can use tools like that on the web. Some of them are available on modern smartphones. We can do inpainting on video. On one hand, it's more complex since we are dealing not with frames, but with sequences of frames. So hence, it's more computationally expensive. But there's something cool about it, since it's not an ill-posed problem. We do not need to hallucinate what's behind the guy on the bike if we want. The guy on the bike when we're trying to remove him from the video, since we know from the past and the future frames what's actually behind him. So that makes it more mathematically appealing problem. And our idea was to make something like that work on a real-time live stream. The use cases could be family-friendly internet streaming. You know, imagine you're a streamer drinking beer or something like that, and you want to just erase it from your live stream. You could have a live sports event where Carlsberg is the sponsor, and some guy comes in with a Heineken beer. We can just erase it. But on video, that's much harder. We pursued the project to gain some knowledge about it, how to do things like that. In huge simplification, it works kind of like that. We have a video at the input, some live stream. We have a detection model that detects the guy on the bike. In our case, we fine-tuned it to work on beer bottles, just because it's a fun object to work with, and it's easy to show. You always have some bottle lying around in the office. It doesn't work only on beer bottles, other bottles as well, you know. Then after we detect it and do instance segmentation, we can put it through inpainting model. That's supposed to remove it. I think we should have called the project object removal instead of inpainting, but the name stuck. So along the way, we encountered many challenges. First of which is balancing speed and performance. With all the beautiful diffusion models that work on images and some diffusion models that work on videos, it's tempting to look at the top-of-the-line solutions, the state-of-the-art that generates prettiest things on the market, and think, we can make it work? No. It's a foolish way to encounter that problem, since these solutions are often not optimized for real-time use cases and are very, very computationally expensive. To run stuff like that, you need many GPU hours to generate something like that. So that's a no-go. But it's still very... it's hard to look away from the state-of-the-art. You know, there's this is an issue at our XVision GitHub repository. Some guy said that it would be awesome to support SAM2. That's like a newest meta model that does video segmentation. And I agree, that would be awesome. It works marvelously, but it's not suitable for real time. To use that kind of model, we calculated we'd have to run it on like a newest NVIDIA DGX server that costs like, I don't know, $1.5 million. So that's not very practical. So speed and performance, can you have both? No. You'd have to try to balance it out, but very often you would find yourself, it's better off to just go for speed and then try to optimize for quality. That's especially important when you're searching for a model architecture with scientific literature. It's best to look for not the best, the state-of-the-art models. When we were searching for a model to work with, our bet was a simpler model from a couple years back, not the newest one, that offered the good baseline results with simple methods that we could work with, as opposed to like newer models that were better but more complicated. Another challenge is benchmarking that kind of stuff. At first, we did empirical benchmarking, which might sound a little foolish, but At first it worked. Every week we gather around and just judged, is our model doing better than the last week? At first, it was easy. We could decide more clearly, but in a few weeks we ran into situations like that where we tweaked the model a little bit and expected some improvements, and we didn't really we couldn't really tell which one was better. So that's turned out to be not really reliable way to do it. Obviously, if you're doing scientific work, like a research, you'd have to go for metrics. You have a lot of things in papers that's like a good measurement of the quality of inpainting. You have peak signal to noise ratio, structural similarity, or some more complex metrics that take into consideration like the similarity between the distributions of features in videos or something like that. They are quite good if you are just benchmarking the model and seeking improvement, but they not always respond to real-world use cases and corner cases, which might be important for your product. Like in our case, the model failed to generate hands or faces, which is like the popular problem with generative AI right now. So while metrics are good to keep track of your progress, they're not enough to develop a good product. Another thing are the efficiency metrics, like these you can see on the right here. They are often measured in ways less strict than the quality metrics. Scientific papers often measure them without taking into consideration the whole more complex system that they would have to run in, like pre-processing, post-processing. We have to run a second model to do the segmentation and that kind of stuff. So you have to take the efficiency metrics reported in scientific literature with a grain of salt. And if we think about a whole solution as a product, we need to test it both using metrics and empirically to on cases that are close to our real-world target. Another challenge is handling streaming inputs. Most models are typically designed to handle static input, like read some data from a file, then do pre-processing, then run the inference, and then do some outputs. That works well for static cases, but if we're doing real-time processing, it's much more complicated than that. It can get messy. For example, if we consider Whisper, it divides the audio segments to like 30-second chunks and just runs the inference on those chunks, then outputs some text as a transcription model. If we want to run it in real time with low latency, we'd have to do it like that, since we do not want to wait whole 30 seconds for inference, But at the same time, we need to put the whole context to the model so it just doesn't break. In the end, we end up doing much more work computationally than normally. So in our case, it works similarly. We have a couple of frames that we need to inpaint, and we have some past references that we need to put in the model anyway and run it every single time. So that's a lot of computation, more than the scientific papers promise you. That's kind of an open problem in transformer architectures in machine learning. They are very expressive and easy to train, but they have a problem. If I have a video model that works on a video with 20 frames of context, I need to process those 20 frames each time, which can be expensive. A recurrent model, theoretically, has a hidden state, and I could get away with processing just each new frame separately and store the hidden state. So there are a lot of scientific works right now that promise us to keep the best of both worlds and propose a better transformer, but so far I have not seen anything reliable. I tried. And finally, we have resource constraints. Basically, when we're working with real-time inference, we need to reduce memory footprint, we need fast computation, and if we're running the model on edge, we need to be energy efficient. Quantization is a simple solution to that since it corresponds to each problem. Why, if we reduce the precision of our calculations, maybe we scale down the weights and activations of the model from 32 bits to, this is like an overly simplified example, but 8-bit integers. We have much less memory usage. Lower precision numbers are faster to compute, and in turn are energy efficient. So that's like an obvious solution. It would be bad to miss on that one. There's also a thing called pruning, which we did not implement in the video inpainting model, but our other project, which we run on the edge in browser. You know, if you have like a machine learning model, some of the layers or neurons or convolutional filters are not crucial to the performance and can be like pruned out without much consequence. And we used a technique called NetAdapt, which is like a very cool framework of pruning the network. You basically start with a pre-trained network, and then and the budget or something like that. Basically, how much latency can you get? The method iteratively prunes some less important convolutional filters or layers from the network, and then measures the latency on a target platform. That's the only reliable way to do it. And then fine-tunes the network to match the performance of what you had in the start. For the video encoding project, we also use video inpainting project. We also use GPU encoding and decoding. Since we already used a GPU, it made sense to just offload the encoding and decoding to a GPU since it does not interfere with the AI inference. There's dedicated hardware for encoding and decoding on a GPU, newer GPUs right now. So that's like an improvement for free. That's especially important if you're trying to decode multiple streams or like a video stream with high resolution. So I'm going to talk about our final solution. For a model architecture, we decided to go with something like a decoupled spatial temporal transformer, blah, blah, blah. It's basically a transformer autoencoder that starts out with a sequence of masked frames and outputs the generated frames. We also employed something like a twin transformer. That's basically an optimized version of a transformer that has effectively reduced its computational complexity from quadratic to linear, allowing us to use a little bigger pictures for inference. We use self-supervised training. For that kind of training, you do not need labels. We just needed videos, and these are like the datasets we used. Some YouTube videos, like the guy throwing a disc or that bunny. And we also tried to include some dataset made for gesture recognition in hope that it would generate better hands and faces, since that was like a primary case for our project. It did not work, but we tried. So how do we train that model? First, we need to sample some frames from a video. Then we generate masks. We mask out some portions of the frames and expect the model to regenerate it. And we just optimize for that. Pretty simple, right? So our final inference pipeline looks like this. We have inputs on the left, outputs on the right. First, we have a segmentation model, which is like the RTM-DET. That's like a instant segmentation model designed with efficiency in mind. You can fine-tune it to work on different objects. We fine-tuned it to work on beer bottles. And we applied the 8-bit quantization and TensorRT. It worked very, very fast. That's like 10 milliseconds. Then we have a neighborhood queue and references queue. We needed to gather the frames in some way to aggregate some of them to be put through the inpainting model, but we also needed the reference frames for the model to work on, like the future, no, not the future, the past reference frames. Finally, we have our own model that we trained. We used Float 16 and Torch Compile to make it a little faster. The whole setup ran in 30 FPS under 200 milliseconds of latency, which by my personal standards, I consider real time. That's good enough for me. I am satisfied. So that's basically it. I will just show you some development process and some problems we encountered along the way. It was messy, actually. It was an awful project to work with, but we learned a lot. It was much harder than expected. It seemed very easy, but running stuff in real time is much harder than running it statically. And I think more of solutions like that will appear in the future, since especially in the augmented reality world. Do you have any questions?
Mate over there has a question.
Okay, thanks. Two questions. The first one is, so you trained this model, if I get it right, on different video streams where these objects have some background. So how resilient is this training to the change of these backgrounds? So what happens if these objects just appear in some other background, like, I don't know, but which the model haven't seen before? So that's question number one, and I will say question number two as well. So you checked also the evaluation metrics from research papers and also did your experimental evaluation. And what do you think, do these metrics coming from research papers reflect well the user experience or describe the situation? How would you consider these numbers being accurate, describing the user experience?
Okay, so answering the first question, the data set that we train on needs to be diverse enough to have different kind of backgrounds in it. It shouldn't be a problem for a model to deal with a background that it hadn't seen before. It depends on a training data set. In our case, it was diverse enough that the YouTube data set. The data set with people showing gestures was kind of boring since we tried to reduce its weight on the whole model. And regarding the user experience, I think the academic metrics are important when doing research kind of work. You need to know if your model improved or not on those metrics, but they do not reflect user experience. I think one of the problems we had during the development of this thing was that we did a kind of a straddle between scientific kind of work and like a product vision for it. So if we are talking about research, we should focus on the metrics. And if we're talking about a product, we should focus on the end user experience. Is it useful? It's not necessarily correlated with the metrics.
Okay, thanks.
Any other questions from anyone? Ali.
Thank you. So how much latency would you need to make a perfect inpainting?
How much latency
would you need to make a perfect inpainting?
I don't think there's such thing as perfect inpainting, but if we had to compare to state-of-the-art models, okay, I think we would need at least 30 seconds of latency. Okay. That's because of not the computational cost, but most models work more statically. They take reference frames from the past and the future.
Okay.
And that's how they can more accurately inpaint stuff. We did not have future to work with, so that was much harder.
Okay. Okay. Thank you.
Any other question? If not, there is one question from me. Because you mentioned about AI on edge devices, and I'm wondering if thus far you find differences in terms of how devices from different producers perform. Meaning, I don't know, Apple devices versus the ones that run on Android and stuff like that.
From my experience as a developer, stuff from Apple is much better in terms of developer experience. The frameworks they have to run AI models on their platform, like MPS or CoreML, are my favorite. I don't think Android has support like that yet.
All right, we have a questions from chat.
Wow.
Patrick asked, did you experimented with comparing differences between GPU and NPU like iOS Neural Engine? In my experience, if most operators are supported on NPU, then inference is faster than MacBook M2 Max GPU.
We did not run that model on NPU back then. I think it would be faster than Mac GPU since we deployed that solution with like a NVIDIA GPU. I don't think a Mac NPU would be faster, but if we were trying to run it on edge, I think that would be our goal to, that would be the first thing we would try out.
Patrick is not physically here with us, so I don't know if this answers his question. I assume maybe he will send a thumbs up on the chat and we'll see how fast the chat. Yeah, thanks for reply. Okay, he's satisfied. All right, unless there are any other questions, let's give a big hand to Wojtek.